Now that we've had the chance to really set the stage with all of the chemical underpinnings that allow us to understand how you go from electrons and protons to an atom, to a molecule, and to a molecule as big potentially as an organic molecule, something containing a lot of carbons and a lot of functional groups. What we're going to start doing now is taking that ability to look at those molecules, how they behave, how they're built, what sorts of reactions they undergo, and see where those pieces show up in biochemistry. And we're going to start with the first big character in our grand metabolic drama, and those are carbohydrates. And so as we go around to meet those, I'm going to start with a brief tutorial on what exactly they are. And so we can start first just by breaking the name down a little bit here. What we see is carbo and hydrate. So carbo referring specifically to carbon. Hydrate, as we've seen a few times, not referring to hydrogen per se, but referring to water. And so one thing that is true of all simple carbohydrates, the ones that aren't yet polymers, which we'll see later, is that they all have a formula that you could represent essentially this way: CnH2O. Taken n times. So in other words, that's going to end up being CnH2nOn. And whatever n is actually going to define one of the ways that we classify different simple carbohydrates. Now, I do want you to notice one thing about this particular formula, and it's the fact that we'll notice we have n carbons and 2n hydrogens. So what that actually means is we have what we would call in organic chemistry, 1 degree of unsaturation. In other words, this is not a saturated substance. I could, in theory, put 2 more hydrogens on something that has this many carbons, because as it turns out, oxygen doesn't interfere with that. We've already seen that once before with this molecule. Notice that adding an oxygen doesn't mean I can get fewer hydrogens on, it just means that this one's got to be attached to the O. But I still end up with 4 H's attached to a single carbon, 2N plus 2. So this 1 degree of unsaturation could be one of 2 things. It could be a double bond, or it could be a ring. Notice that when we've seen things with formulas like C3H6, there are 2 ways I could possibly end up with just twice as many hydrogens as carbons. One of them is to put a double bond into the structure. The other is to loop it around and make it bond to itself. Now, in the case of carbohydrates, we're going to see that we actually have one in one form and the other in the other form. So I'm going to go over to the first page of the carbohydrates lab that you'll be doing and illustrate that to you. You'll notice that over here glucose and xylose are shown in their straight chain forms, and what both of them have at the very, very end of the molecule is a CHO, which I'll remind you is in fact a way of writing this. In other words, what I've got here is an aldehyde. Now this could cut either way. We're going to see some sugars that have their C double bound to an O at the very end. We'll see others that have it in the middle of the molecule. And in that case, they're going to be something with a ketone present. But either way, that gets you the 1 double bond. And so anytime you're looking at the straight chain form of a carbohydrate, it's going to have a carbonyl in it. The only question is it somewhere in the middle or is it at the very, very end? And that will define it as being an aldehyde or a ketone. Now, these others you'll notice are shown in their ring forms. And we're going to learn how to do both of these projections, but the ring form is just going to have a bunch of OH groups on it. Won't actually possess any of the aldehyde or ketone chemistry because in this case, the extra bond is the one that loops the entire thing together. So you're going to see one or the other as we go through this, either a double bond or a ring, depending on which form of the carbohydrate you're looking at. Now, I mentioned there are some bits of classification that we do, and some words we're going to start throwing around very rapidly, and so these are worth getting to know. One way we classify these is on the number of carbons in the carbohydrate. In other words, if you're looking at my original formula up here, the value of n. And so what we'll see here is that when something is n equals 3, which is just one particular sugar, n equals 3, we would call any sugar like that a triose. So notice tri for the 3 carbons. Ose is something you're going to notice as the ending of pretty much any sugar that we encounter, unless it's gotten some sort of special trivial name first. So triose, 3-carbon sugar. And so that would be something like this. And this right here is glyceraldehyde, and it is the only triose in existence. Now, what we're going to see is that as we go to larger and larger sugars, there are going to be more and more options. When I get to n equals 4, tetrose, right? So just like tetrafluoro something, we're going to have here tetrose for a 4-carbon sugar. For these, there are going to be 4 of them that exist. 2 of them are mirror images of each other, and if that piques your intrigue, you're going to really, really enjoy the next video all about stereochemistry of these things. N equals 5, you can probably guess, would be referred to as a pentose. There are 8 pentoses, and there are a whopping 16 hexoses. And I should also note that I am specifically referring to the number of each of these things that exist in the form with an aldehyde at the end. If you start incorporating all the ones with ketones, that number is going to swell a little bit. But we'll be looking first and foremost at the ones that have aldehydes in them, because glucose, the most important one to us, is one of them. But that's one way that we classify these. And so you will frequently hear this sort of reference to pentoses, hexoses. Tetroses are a little bit rarer in biology. Trioses, pretty much a curiosity for us. But we see a lot of both of these present in biological settings. So that's one way that we're going to be classifying them. The other, and I've been alluding to it already, is going to be by functional group. And so, for example, we've already examined that you can have an aldehyde in a sugar, and when you do, we're going to call that particular sugar an aldose. Similarly, you might guess then that if I have a ketone in my sugar instead, we're going to name that a ketose. And so to give you a sense of what those might look like, as we said, glucose and xylose here are examples of aldoses because they have this CHO sitting there at the very end of them. So there are my aldoses right there. On the other hand, fructose over here, give it a different color. Fructose has a ketone slapped in the middle of it. Notice how that carbon is between a pair of other carbons. So fructose would count as a ketose, glucose and xylose, both aldoses. Now, the last bit of classification we have won't be for these monomer sugars. So these are the simple sugars, the ones that are just a single molecule, either straight chain or in a ring. What we're also going to see is that you've got complex carbohydrates. In fact, we eat a lot of these. Most of the glucose we get is in the form not of simple glucose, but in a dimer, in a disaccharide. And so what we'll see here is that you have monosaccharides. That's what we've been talking about so far. And as that might sound like, that's one sugar molecule. These, for certain, will have this CnH2nOn formula. So C5H10O5, C6H12O6. They'll definitely have that formula. We're also going to see a decent number of disaccharides. And so, as you might guess, that's going to be 2 sugar molecules. And they will be condensed with each other. So if you remember the condensation reaction from last time around, that reaction kicks out a water molecule. So in actuality, all of these will all have this formula instead. So you won't have Cn and then H2nOn. What you're actually going to have is H2n minus 2, O, n minus 1, because you will have lost a water molecule in the process. So for example, sucrose has this sort of formula. Sucrose is a very common disaccharide. This is a dimer made when a fructose molecule and a glucose molecule are condensed with each other. Some others that you might be familiar with, along with sucrose. Very likely that you've at some point heard of lactose. That is another disaccharide. These are just a pair of them. We'll go ahead and put etc. at the end of that because there are plenty more that exist, because you can pretty much pair up any two sugars or two of the same sugar and make something a little different that might have a slightly different level of sweetness, may or may not be digestible by human beings. In fact, lactose is an interesting one because we frequently are born with the enzyme to deal with lactose and then bit by bit stop producing it. And so some people later in adulthood develop lactose intolerance because they can't actually split that one in half to get the two sugars. More of that to come when we begin looking at the reactions of these sugars. Next up, you have oligosaccharides and polysaccharides. Both of these mean multiple sugars, but in general, we use oligo to correspond to a few, whereas poly means a lot. And we're talking like thousands of sugar molecules